And 8.3 is all about a special kind of Markov chain called the regular Markov chain. Ugh. Sorry, there we go. It's called a regular Markov chain. So we're sort of continuing from where we left off last week with Markov chains. We're going to look at a special class of Markov chains called regular ones. I don't know why they picked the name regular. It doesn't really describe anything. If you do enough math, you'll see this word regular or like normal and stuff everywhere. It's an abused word, so I don't think it really means anything. We're just going to call these regular, and why that's the name we choose, I don't know. I didn't name them. You can pick that fight with someone else. But anyway, we're going to talk about something called the regular Markov chain, because they're a special class of Markov chains that we can sort of easily understand, and they have some nice properties. And so we're going to see what those properties are and then use it to solve some certain problems that are peculiar to this type of Markov chain. So that's where we're going in this section. So before I can tell you what a regular Markov chain is and what it's all about, let me just recall a definition that I gave at the end of class last time. And I'm picking all the bad markers, apparently. Try this again. That's much better. And I'm not trying to write the word regular, I'm trying to write recall. So let's recall. I told you guys what a probability vector is. So just to remember what that is, a probability vector is just a vector. So when I say a vector, of course, I mean a row or a column vector. I mean a matrix with either one row or one column. So probability vector is a vector whose entries add up to 1. And are also not negative. So the numbers in the vector can't be negative, and they all have to add up to 1. So the idea is that the entries in the vector represent probabilities in some situation, in some experiment. So here's an example. Again, I wrote something like this on the board last time. Here's a probability vector with 3 entries, 0.2, 0.3, 0.5. Those all add up to 1, and none of them are negative. So this is a probability vector with 3 entries. And again, I've mentioned this before. If we look at the transition matrices that we were computing for the Markov chains last week, the transition matrices, the k-step transition matrices, every row of one of those is also a probability vector. So the rows are probability vectors in a transition matrix because the rows add up to 1. Okay, so what we're going to be interested in this section is a special kind of probability vector. And the only reason it's really special is because we're going to associate it to a Markov chain in a certain way. And these are called state vectors. So I guess I should be a little more clear. We're actually going to be interested in a couple of different kinds of probability vectors in this section. And one of them is just called the sort of state vector. It's the most general thing we'll be interested in here. Later, we'll have something called a stable vector. But let's not get ahead of ourselves. Let's define a state vector. So a state vector, oh, actually, I don't want to state it this way. Let me state it this way. First, we need a Markov chain. So suppose we have a Markov chain. I have a Markov chain, and it has, say, n states. So n is just some positive number, positive integer, representing the number of states that I have in my Markov chain. So, we've had many examples of Markov chains now. The first one that we dealt with really was this weather example where there were 2 states, rainy and sunny. So it might be good to have that in mind as we go. So maybe n is 2, right? But it's some positive integer. So I have a Markov chain with n states. A state vector, this is what I am defining as a state vector. State vector, and I accidentally crossed out the word instead of underlining it. A state vector is a probability vector. And I don't know, let me just give it a name so I can talk about it for a second. So maybe my probability vector is called x, and the entries are x1 up through xn, 1 for each state of my Markov chain, where xi is the probability of being in that state, of being in state I. Okay. This is a state vector. It's just a particular probability vector that I'm going to associate to a Markov chain, where I have an entry for each state of the Markov chain, and each entry represents a probability of being in that state. That's all. So the first entry is the probability of being in the first state, and so forth. Okay. And right, so I mean, this is a state vector. So what's nice about this is we're going to relate this to this k-step transition matrix. What we should keep in mind is when I told you guys about Markov chains, I always sort of emphasize the fact that we need a starting point, right? Like in our rainy, sunny example, I couldn't just tell you out of nowhere what the probability of rain or sun is. I needed to know what the weather was today so that then I could tell you about the probability, say, 2 days from now, right? So I need to have like a starting point. And so that should sort of jive us the wrong way when we read this definition, because probability of being in a state, well, yeah, but like when, right? It seems like I'm sort of pulling probabilities out of the air here with this definition. And the idea is we're going to sort of get around that. What's going to basically end up happening is I'm going to be able to represent a starting point, like it's sunny today, with a state vector. And that'll give us sort of a starting point. And we'll see other examples where it's sort of we'll have a sort of a wishy-washy starting point, where we won't know for sure which state we're starting in, but there's certain probabilities that we'll start with. So this will become more clear as we go through some examples. But the point is that we'll still have a starting point to deal with. And then from there, we'll be able to find all other state vectors after we have our starting point. So as is always the case with Markov chains, we need to start somewhere. I need to start somewhere. Okay, so I just wanted to point that out about this definition. It doesn't seem like we have a starting point built into it, but we'll see that it'll all be okay. Okay, so before I give an example and do some of that, I want to just state one more, I want to state a fact about state vectors. So, you know, your book will call this a theorem because that's the fancy math word for this. But I basically just mean fact. Here's something that is true. Well, I won't prove that it's true, but here's something that is true. If xk denotes the state vector of a Markov chain after k transitions or steps, if you will, after k transitions, then we have the following fact. And before I write it down in fancy math terms, all I want to say is that all that I'm about to say is that the state vector after k many steps can always be found by just applying the transition matrix, say k many times, to some starting vector. So the idea is this: xk, maybe plus 1, is equal to xk times the transition matrix p. So p is the transition matrix. I've been using that same notation for it, p. Okay, so the idea is if I want to know what does the state vector look like at the k plus 1 step, all I have to do is take the state vector at the k step and multiply it by the transition matrix. So if I give you some initial state vector, how do I find the probabilities of being in each state after one more transition? Well, I just apply the transition matrix once. I just multiply it with that state vector once, and that'll get me to the next step. And so we see that really I'm going to be able to get all of the state vectors just from one. So, you know, in particular, we have this fact. xk is really just take some initial guy that I'll call x0, my initial state vector, and multiply it by the transition matrix k times. So p to the k power. So this is really what I want to say with this fact. This is what I really want. This is the heart of the matter here. Is there a question? Like someone's mic was on. Maybe not. Okay. Well, if you guys have any questions, please let me know. Anyway, so to get to the state vector for after k many steps, all I have to do is take whatever my initial state vector is and apply or multiply by the transition matrix k times. So basically multiply by the k-step transition matrix. Okay. So we see again that these matrices are coming into play in a big way. They're very helpful for us. Okay. So this is going to be a very useful fact that we're going to use a lot in this section. So let me do an example to sort of clarify some of this, just to see how it works in practice. Put all of this together. And I'm going to go back to an example that we've already looked at, which is this weather example again, just because it's good to have something that we're familiar with. So, so we have our weather example. So if we remember, there are two states. Either sunny or rainy. Sunny or rainy. And we had this transition matrix. We found this before. The transition matrix was 3/4, 1/4, 1/3, 2/3. And I had labeled it so that it was sunny, rainy, sunny, rainy. So this is our transition matrix. And these were the labels so we could make sense of these numbers and what they represent. Okay, so this is my transition matrix. And I had answered the question before, what is the probability that if it's sunny today, it's rainy 2 days from now? So if it's sunny today, what's the probability that it's rainy 2 days from now? I've answered this question before. Oh, I suppose I forgot to write the word rainy. Rainy 2 days from now. So we've answered this question before. And I'm basically going to answer it again, but now we're going to sort of use it in this new language with a state vector and all that. So we're going to see how that'll work. So what's the idea? I am basically looking for x2 in the language of that theorem. I'm looking for the state vector after 2 steps because I'm asking for 2 days from now. So I'm really looking for x2. And according to that theorem, I need to take x0 and multiply it by p squared. By p squared. Yeah. Okay. So I can find p squared because I can just take the square of this matrix. That's no big deal. What's x0 though? This needs to be what we might call the initial state vector. Your book might use this word. I'll use this word. It's just going to be my starting point, basically. So what's my initial state vector? Well, it's going to be a vector. It's going to have 2 entries because there's 2 states. And those entries have to represent the probability of being in each state initially, right? But before anything has happened. So I need to find those probabilities. And so maybe the first one is sunny and the second one's rainy. I need to answer initially, what's the probability of it being sunny? And initially, what's the probability of it being rainy? Well, what's our situation that we're considering? We're considering the fact where it's sunny today, i.e. initially it is sunny. Without any doubt, it is sunny. So if I was assuming that it is sunny and not rainy initially, what does that mean probability-wise? Well, what's the probability of it sunny? Well, I know that it is sunny, so the probability is 1. There's no doubt it has to be sunny because that's what I'm assuming. What's the probability of rain? Well, it must be 0 because these have to add up to 1. This is a probability vector. So here is my initial state vector. It is 1, 0, representing that it's definitely sunny and it's definitely not rainy, right? Okay, so there's my initial state vector. So now that I have this, I can easily find x2 by just taking this row vector and multiplying it by p squared. So I'll go ahead and do that. So let's find p squared. So maybe I'll erase this.